Would you raise your hand if you got that one? Good for you, fantastic. Integrals versus derivatives so far. Easy or harder?
Harder.
Harder right now. You'll get used to it. Now let's look at the next question. Find the equation of a curve. Well, you better get used to it. Find the equation of a curve such that the slope at each point is x squared. Let's think about what this means. Find the equation of a curve such that the slope at each point, is x squared. What gives you the slope of an equation? So basically it asks this. Give me an equation so that when I take a derivative of it, the derivative is x squared. Do you got me? That's basically asking for the antiderivative. That's what this question asks. It says, give me an equation so that when I take a derivative of it, when I get the slope at any point, that's a derivative. That's going to give me x squared. So this question says, okay, here's what you know. The slope at each point, recognize that's a derivative, right? The derivative means a slope at any point. That is dy dx. The slope equals x squared. True? The slope equals x squared. How do you undo that? Well, how do I find the equation that's going to give me that? Take an integral of x squared dx. You're going to notice some weird things, and this is kind of the way it works. It's interesting. I can show it to you a little bit later where all these symbols come from, but do you notice something? This is weird. But you notice something about this? If I treat this like a variable and I multiply, I get dy equals x squared dx. Do you see where the dx is? Interesting, huh? If I want to undo a derivative, an integral undoes that. An integral undoes that on both sides. Integral of dy is y. Aha! Look at that. That's 1 dy, right? With respect to y. 1 dy with respect to y will give you y. Does that make sense to you? Did I lose you?
Yeah.
Do you remember I lost you?
Yeah.
What was this?
I don't know.
No. What was this?
Oh, x.
Clearly. With respect to y, it is y.
Oh.
Equals the integral of x squared dx, which is exactly what we have right there. That's very interesting. It says undoing a derivative gives you an integral. Crazy? Crazy. Very cool. Anyway, that was a side note, beyond a little bit of the realm, but it's interesting how that works, right? Because some of you were asking, where's the dx, or maybe thought, where's the dx coming from? Why do we have that? It's from doing that. Doing this idea, undoing a derivative, says, well, you work it this way, integral of 1 dy, that's y. Take an integral of both sides, you get an integral of x squared dx. Okie dokie, that works. Cool. Okay, now back onto this. Did you need that? Did you want me to write that back for you? You have it, right? Hey, it's on video. You can watch it again. What is the integral of x squared dx?
X to the third plus c.
So you saying that that's the equation, right? That's the, what does that represent right there? The family of curves, or function, the family of functions, I guess, the function family. So that when I take a derivative of that, it's going to give me x squared. Is that true? For sure, any constant. Now, can I be specific? Can I give the equation in this terminology? Can I do that with this problem right now?
No, not right now.
Not right now, because I haven't been specific on the C. But if I change the problem just slightly, and here's what I'm going to add on to it. I'm going to say, let's find the equation of the curve such that the slope at each point is x squared, and that's why I add the dot, dot, dot. Given that it passes through the point 2, 1. Given that it passes through 2, 1. You know what? It doesn't make it any harder. It really doesn't. What this says right here is this family. All the x cubed families you can think of, right? It says any of them that are shifted up and down along the y-axis. Do you notice that? There's no other x's. This is just x cubes shifted up and down the y-axis, so where your y-intercept is different. What we're saying is now, choose a specific one and now tell me what it is. So the way to go about this is you say, all right, well I know for a fact what we just found out is that y equals x cubed over 3 plus c, not e, c. Right? That's what we have. Hey, do you have an x? Do you have a y? Plug them in, you're going to be able to find c. That gives you a specific equation, not a family, but a specific equation. So when I plug in my 1 for y, my 2 for x, let's just solve for c. If I subtract 8/3 from both sides, what do we get? Negative 5/3, something like that? Yes, no?
Yes.
So when I do that, I get c equals negative 5/3. Can you see that down there? How do I finish up the problem? Well, it's not that hard. It's you now know what c is, right? Here we were stuck without a c, so if I want to finish this off, I go back up to here, I say, all right, I know the equation, so that when I take the derivative of it, it gives me x squared when that happens, and it goes through this point, it's y equals x cubed over 3, and then what? That's right. Let's verify that for a second. Is this going to go through the point 2, 1? Sure, that's how we found c. When I take a derivative of this, does it give me x squared? Then this is the only equation, so that when I find the slope at each point, it's x squared and goes through this. That says it's not a family anymore. We've narrowed it down to one of these graphs. How many will feel okay with that one? That's the idea. This is very similar to what's called an initial value problem that we're going to study right now. We're going to talk about differential equations, just an introductory, not anything too drastic. They have a whole class on differential equations, right? I'm giving you like, you know when you get a new thing of ice cream and you open the lid and you get the ice cream on the top, you're like, oh, I better get that stuff because it melt real quick. You know that? The ice cream is differential equations. I'm giving you the stuff off the top. That's it. That's the skimmest tasting of ice cream. It's really sweet, but you get more of the good stuff in the actual class, okay?
Yeah, it turns bitter.
Oh, it turns bitter. It's fun.
Depends on what kind of ice cream you're talking about. Depends on what you consider fun.
You ever had garlic flavored ice cream?
It's actually pretty good.
It's not like that. It's an acquired taste.
Garlic ice cream. I have 3 semesters from there, so I'm worried about it then.
Yeah, so don't go home and say, oh, I learned all about differential equations. No, you didn't. All right, this is just a little teeny bit of it, but the idea is there. And we're starting with a basic idea. Let's pretend for a second, and this was basically it. I'm just kind of going to illustrate a little bit more. Let's pretend that I have a derivative that I know, like that. The idea is this. It's basically the same thing we were doing here. It's, can you find a function, an antiderivative, so that the derivative gives you this? The idea is, you know what, maybe write it a different way. I don't think I need that there either. That'll make it easier for us. The idea is basically the same thing. If you know the derivative is f of x, can you find an antiderivative, basically, a function so that when I take the derivative of it, it gives me our original function back again. That's the idea. It's essentially the same as this. Let me show you how this works with what's called an initial value problem. After we do one basic example. Let's say that dy dx equals x to the fourth. Can you tell me what y equals? If the dy dx equals x to the fourth, can you tell me what y equals?
1/5 x to the 3.
That's what it would be. It's the same question here. Do you see how it's the same question? It's interesting, isn't it? Same thing I asked you here. Find me an equation so that the slope is this. That's what it says. Find me an equation so that the derivative is this. Instead of slope, I now have the word derivative. But it's the same idea because slope is a derivative. So here it says, well, I know that y is going to be the integral of x to the fourth dx. If you want that proof again, here's the proof again. Well, not even a proof, but here's a manipulation of these variable parts. If I separate them, I get dy equals x to the fourth dx, yes? To find y, I have to undo a derivative on both sides. Undoing a derivative is called an integral. The integral of 1 dy, I can put a 1 anywhere that I want to. The integral of 1 dy is y. The integral of x to the fourth dx is exactly what I have here. And that's why we're coming up with this. That's how you find the antiderivative. That's that. Does that make sense to you? Can you follow that? Have I blown your mind like a mind grenade? Are you with it?
Yeah.
All right. And Joe was right. X to the fifth over 5, or 1/5, x to the fifth plus c. Don't forget the plus c. So, what's a solution to a differential equation? It's actually not one. It's solutions to differential equations, just like we have solutions for a family of curves before I put this little piece into it. So the reason why I gave you this first is because this problem is a differential equation. It's asking the same concept. This right here is a differential equation. That's a family of curves. You got it? This right here would be an initial value condition, and that's what I'm going to introduce to you over here in the terms of differential equations. So, both questions are the same. Give me the slope, give me the derivative. Give me the slope of, if the slope is this, find me a function so that the slope is what I've given you. Find me a function so that the derivative is what I've given you. It's the same exact question. Then I can add pieces onto it. Here's a condition that lets you solve for C. I'm going to give you an initial value problem that lets you solve for C. Would you like to see one of those?
Totally.
That was funny.
I think it's- I'll leave that. I'll leave that. This is basically when you only need one solution based on some initial condition. So this is a family of solutions right here. We're going to say, well, we only need one. We need something to fit a specific purpose, and that's what we're going to do here. So basically, here's an example. If you have